Thank you very much for the kind words there, Michael, and to all the attendees from coast to coast in Canada, as well as in Greece and anywhere else that you may be participating in this webinar. And I hope that everybody's keeping safe and healthy, especially during these days. So yes, my name is Nicholas Vlahopoulos. I'll be talking about the Eupalinos Tunnel. Okay, so I'd like to thank the Tunneling Association of Canada, TAC, and the Greek Tunneling Association, GTS, for inviting me, first of all, to give this webinar presentation. And the topic was suggested by TAC, and I'm very happy to present on this topic that has to do with Greece and civilization. And a lot of people have been working in the backdrop in order to make this webinar happen, and I'd just like to acknowledge them here, and I'm truly grateful to them for their time and efforts. So thank you for that. And I'd also like to thank the organizations that I've been collaborating with for over 2 decades in Greece, primarily the National Technical University of Athens and the Aristotle University of Thessaloniki, as well as the Hellenic Society for Soil Mechanics and Geotechnical Engineering. Now I'd like to say a few words to my Greek friends and colleagues that may be participating in this webinar as well. Θα ήθελα να ευχαριστήσω θερμά την Ελληνική Επιτροπή Σειράγγων και Υπόγειων Έργων για την πρόσκλησή τους. Με τιμή απεριόριστα το να είμαι μαζί σας σήμερα για να υποστηρίξω την εξαιρετική προσπάθεια που γίνεται όσον αφορά στην υποψηφιότητα της Αθήνας για το World Tunneling Congress το 2023 από την δυναμική και δυνατή ομάδα του κυρίου Φίκη, αλλά και να παρουσιάσω σχετικά με ένα θέμα που με αγγίζει τόσο για το γεωτεχνικό όσο και σαν Ελλάδα. So Athens has put together an excellent candidacy bid for Athens to host the World Tunneling Congress in 2023. And with the competent, dynamic, and strong team that has been assembled under the leadership of Mr. Yannis Fikiris, please consider visiting the site and supporting the Athens WTC 2023 bid, as you can see here. And we truly hope to see you in Athens at that time. In terms of a presentation outline, this is basically going to be the outline here. I'll give you a little bit of a historical background, talk about the tunnel alignment, some design and construction details, the geology, the meeting alignments, a summary, and a discussion to ensue. And so as we begin, I just wanted to share some initial details associated with this UNESCO designated heritage site. The length is approximately 1 kilometer long. The interior dimensions of the tunnel itself are 1.8 by 1.8 meters. The overburden at the greatest depth is 170 meters. And the tunnels were bored from the 2 ends and met in the middle with 1.8% accuracy. The excavation took approximately 10 years, and it was in use for approximately 1,100 years. And so the Eupalinos Tunnel is located in present-day Pythagorean on the island of Samos. It's the same island as the birthplace of Pythagoras that you can see here, and he lived from approximately 570 BC to 496 BC. And many of you are certainly aware of the Pythagorean theorem that is used in geometry. And so how do we know? How do we know about the Eupalinos Tunnel? Well, we have it cited by Herodotus, who was an ancient Greek historian, and he lived between 484 BC to 425 BC, and he's known for having written the book the Histories, or Inquiry, or Historia, which is a detailed record of his inquiry on the origins of primarily the Greco-Persian Wars. And he's widely considered to have been the first writer to have treated the historical subjects using a method of systematic investigation. So the Eupalinian aqueduct is described by Herodotus in the Histories in section 3.60. And you can see the quote here. I have dwelt longer upon the history of the Samnians, or the people that live in Samos, than I should otherwise have done, because they are responsible for the greatest building and engineering feats in the Greek world. A tunnel nearly a mile long and 8 feet wide and 8 feet high. And this work was the work of a Megarian named Eupalinos, the son of Nastrophos. And without this insight by the histories and Herodotus, the tunnel may not have been discovered in the present day. And so, who was the first, or one of the first, to do this simultaneous bore from both ends? Well, Herodotus gives us this insight, and Eupalinos, or Eupalinos of Megara, which is a historic town and a municipality in West Attica near Athens, was an ancient Greek engineer who built the tunnel of Eupalinos on Samos Island in the 6th century BC. No other real record exists of his life other than the mention in the histories by Herodotus. However, it's one of the greatest engineering achievements in ancient times, and it's a water tunnel which is approximately 1,036 meters long. And so the Eupalinos Tunnel, or the aqueduct that is referred to in literature, is located in Greece at the northeast boundary of Europe in the present-day Balkans, as you can see here. It's on the Aegean island of Samos, as denoted by the white circle on the map here. So Samos is the 8th largest Greek island in the Aegean Sea, with an area of less than 500 square kilometers, and it's separated from Asia Minor by a narrow strait, the Strait of Mycale. Samos historically flourished in the 6th century BC during the reign of a tyrant called Polykrates, he lived between 570 and 522 BC, and his court attracted poets, artists, musicians, philosophers, and mathematicians, as well as other learned peoples from all over the Hellenic or Greek world. His capital city, also named Samos, which is the present-day Pythagoreon, which I showed before, it was situated on the slopes of a mountain called Mount Castro, and you can see Mount Castro here. And it was on the top of the slope of this mountain, and a dominating natural harbor that was facing the straits towards Asia Minor. Now, Polykrates was the tyrant of Samos between 540 and 522 BC. He had a reputation as a fierce warrior and an enlightened tyrant. Now, tyrant to most of us might not seem as an applicable term, but tyrant is derived from the ancient Greek tyrannos, which is the absolute ruler who's unrestrained by law and who has the legitimate ruler's sovereignty. So it has a negative connotation in the present day, but that stems from the fact that such rulers oftentimes used oppressive means to rule. He had to fortify and protect his kingdom from pirates, and you can see the walls around Samos here in the fortifications denoted by the red, and he had to protect his city from the pirates and others. So thus the requirement for the fortifications to protect the city, but also to bring water into the city as well. And so here we see kind of the topography of the area. And there's a natural river to the north here, Agiadis, and it's to the north of the fortifications. And Polykrates needed to provide water for the flourishing population that he had in his cities. And as such, he decided to bring water from the north, from the Agiadis River to his city, but again, needed to protect this water source. And so here we see the alignment, or the gross alignment of the tunnel can be seen stemming from the north entrance to the north, and then the south entrance to the south here. And again, it's approximately 1 kilometer long that passes under Mount Castro. Here we can see the tunnel alignment in cross section. It's 1,036 meters long, 170 meters of overburden. We have the excavation from the north, the excavation from the southern portal that were excavated simultaneously. And the breakthrough point was basically right under the highest point of Mount Castro. So how was the construction and alignment of the tunnel achieved? Well, no one exactly knows how Eupalinos accomplished this, but most scholars seem to agree that the most probable explanation is the use of Hiro's method. And Hiro, who lived in ancient Alexandria in the 1st century AD, i.e. 5 centuries later, founded the first organized school of engineering in Alexandria and produced a technical encyclopedia describing early inventions, technologies, and mathematical solutions. So the Eupalinos Tunnel is considered as the first underground project excavated with a geometry-based approach. And so using Hiro's method then, one needs to start at a convenient point near the northern entrance and of the tunnel and traverse it towards the west to come down to the southern portion. So we traverse the western face of the mountain along a piecewise rectangular path that's indicated in the red here at a consistent elevation above sea level until reaching another convenient point of entrance near the southern entrance that we can see here as well. So this particular map is part of a detailed, comprehensive 250-page report published by Hermann Knast in 1995 of the German Archaeological Institute of Athens. And so, therefore, using Hiro's method, if one was to measure the total distance moved west, then subtract it from the total distance moved to the east, one determines the leg of the right triangle that's shown in the dashed line here. And the triangle's hypotenuse along the proposed alignment here is the triangle's hypotenuse. So then one can add the lengths of the northern and southern section as we do piecewise here along the lengths. And you can see it as the dashed lines. And once the lengths of the two legs are known, even though they're buried between the mountain, one can lay out smaller horizontal triangles on the terrain with all three hypotenuses on the same line. Therefore, workers can look back to the markers along these lines here so that they can make sure that they're excavating in the right direction. But let's, and we'll take a closer look at that in a second, but let's remember here that we're at the 6th century BC. So here we have no magnetic compasses, we have no surveying instruments per se, or before, we've had no kind of history of surveying instruments being introduced, and no topographic maps of the area at the time. So perhaps the instruments that were used were as such: crude carpenter tools that we can see here, made of batons and pins, in order to measure the right angles that are required to navigate around the north entrance to the south entrance. And perhaps Hiro in the 1st century also describes the use of the dioptra, which we can see here, to measure angles. So it was a surveying instrument which was suitable for the precise measurement of horizontal, vertical, and angular distances between either two celestial bodies, if we're going to use it for astronomy rather, or if we're going to use it between two terrestrial points. So it consisted of a stand which had a horizontal tooth base, you can see here, and that could be rotated with the help of an endless screw. And it was a precise system of aiming, kind of like a modern-day theodolite or total station. And it could be placed on the base of it. And this disc was placed at the edge of a semicircular disc and had cross cuts or crisscross turning aiming devices, and the operator of the instrument could aim it to any point in space and mark their angular position. So taking a look at the geometry then, or a closer look at the geometry associated with the alignment then, one can use the alignment along the tunnel within the mountain and determine how to site it from the outside of the tunnel versus the inside of the tunnel so that we can start the works. And so here we see the northern alignment and the geometry that exists. And so maintaining the tunnel alignment and respecting its geometry, one can then determine the alignment outside the tunnel in this fashion. One can respect the X and Y lengths that correspond with the angles within the ABC triangle of the global configuration that we see as part of our geometry. And so, having determined the alignment outside that is required of the northern entrance, one can then establish guides or markers along this alignment in order to monitor the construction work. So you can see the guides and the markers here along that predetermined or calculated alignment. And we still use these boning rods or batter boards for surveying construction stakeouts to this day. And honestly, they look quite familiar to what we're seeing in this photo here. And so the guides act as a point of reference in both directions. So as the tunnel is being excavated, one can check the alignment from the tunnel as a back bearing, as we can see here. So if we were to excavate here and looking back, we can guide ourselves and make sure that we are still in alignment with the guides or the markers that have been established outside. And also from the outside, while the tunnel is being constructed, the guides could also be used to check the alignment with the surface alignment of AC, because over the alignment AC, there was also a tunnel alignment that was established. Okay. And we can determine that straight line, i.e. the hypotenuse of this triangle ABC. So we can establish that line there and make sure that we're on that same alignment. And within the tunnel excavation itself, lamps, as you can see in this picture here, were used and placed on the floor of the excavation along the center line to guide the construction works. In terms of horizontal control of the tunnel excavation, chorobate could have been used. And the chorobate is an instrument that is 6.5 meters wide, or long rather, with a 2-meter portion that was filled with water. And the water was used to ensure that the instrument was level. And as such, one could look through the apertures at these locations A, line them up, and make sure that the apertures were aligned while also focusing on a particular point of interest. Okay? So in this case, the alignment of the tunnel floor to make sure that it's at the elevation that we require it to be at. So alternatively, the chorobate could be placed on the base of the dioptra that we saw before. A simplified and animated presentation of the construction of the project and of the processes used was also prepared by the Association of Ancient Greek Technology Studies. And that was under the supervision of Professor Tassios. And that can be viewed in the link that's provided here within the presentation itself. It goes through the related concepts that have been introduced within this presentation as well. If one is interested in seeing these ancient instruments, including the dioptra and the chorobate, that may have been used during the construction of the Eupalinos Tunnel, then I highly recommend the Kostanas Museum that is located in Olympia, which is the birthplace of the Olympic Games. There's also a Kotsanas Museum or Kotsanas Museum located in Kolonaki, Athens, in Greece as well. It's really a fascinating museum with multiple displays of ancient Greek technology, and many of the devices aside from the dioptra and chorobate that were used and created by Archimedes. So Archimedes of the famed the Archimedes principle between 287 to 212 BC, was a Greek mathematician, physicist. He was an engineer, an innovator, as well as an astronomer. As well, you can see here that a copy of the famous Antiquity calculating mechanism akin to a modern day computer is also housed in the museum. So here, for instance, is the display for the diopter at the museum, and I apologize for the quality of the photos as they were taken with my cell phone in 2017. But one can visit the museum virtually using the link that's provided here. And it'll take you through all of the displays. Quite a good interactive virtual museum visit. So these same principles are applied today. An example of this is the Hellenic lignite mine. And these are still applicable today as they were 2,500 years ago. As part of ongoing collaborations with Greece spanning 2 decades, our graduate students at the Royal Military College of Canada, as well as Queen's University, have had the privilege of participating biannually in graduate field trips involving large-scale geotechnical works and underground construction sites throughout Greece as part of the graduate programs of the National Technical University of Athens, as well as the Aristotle University of Thessaloniki, primarily with professors Paul and Vasilis Marinos. One of the sites that we've visited multiple times in the past is the lignite quarry in northern Greece in Servia, Kozani, that you can see here. And this is a large-scale lignite mine whereby mining takes place as an open pit combined with underground excavations. And one can see the tunnel or mining portals here as well. So we have an open pit, but we also have mining entrances as well underground. And of note are the instrumentation platforms or the bases that sit at the front of each one of the mining entrances here. And if we were to take a closer look at this here, one can place surveying instrumentation, i.e. a total station, a theodolite, a level, etc., on this platform with a view of monitoring the construction that is taking place. So one can monitor the alignment as well as the opening of the tunnel to make sure that the dimensions of the tunnel are also correct according to specifications. The geodetic location of the pedestal can also be used to establish horizontal and vertical control, i.e. a point of horizontal and a vertical reference within the tunnel as well. And here we see a PhD student of mine, Henry Helmer Smith, looking and checking out the alignment here. So the fundamental principles are still applicable today as they were 2,500 years ago. The instruments may have changed, but the principles are definitely the same. Fascinating. And so no tunneling activities occur without the use of surveying instruments and techniques. We also have other techniques that we employ in tunnels as well. For instance, we've got geophysical techniques and LiDAR that you can see here, a laser sensing technology that can be employed within the tunnels themselves. So for those of you that may not be familiar with surveying, here's a simple example to put things into context. It takes place on the grounds of the Royal Military College or University of Canada on the parade square. And if we have a known point, we can use a certain projection or horizontal reference system to determine specifically where that known point is within an acceptable error on the planet itself. And so we use a benchmark to determine the vertical position at a location. In simple terms, we have a known point of reference here. From that known point of reference, if we need to determine the position of other known points, let's say the corner of the parade square there, we can use the coordinates of the known point to find those other positions. And so what do? We can take these points and we can establish where they are, and using point A and B as an example, we can place instruments or prisms or targets on point A and B, and on the known point, we can place a total station or our instrument that is able to determine angles and distances. And what we can do is we can shoot onto these 2 points. We can determine the distance between the 2 points, the distance to the points rather, and we can also determine the angle A. So the relative angle between the point A and the point B. Once we do that, we can use some coordinate geometry or even a Cartesian system in order to determine where our known point is and then where the new point may reside. And so in this way, we're able to determine where the position is of that point. And if we were to take a roaming prism that we can say here, we can roam around any type of detail or any type of structure, and we can make maps relative to the known point and reference system that we have. So therefore, we can use survey equipment in this fashion at tunnel construction sites as well. So we can determine along the alignment of the tunnel, where the tunnel will align and where we need to turn the tunnel or give it its direction according to its alignment. But we can also use tunnel wall survey targets that can be seen here, and we can reflect the total station or shoot onto these targets to determine the distances and the openings of the tunnel opening to determine if any convergence is there, so that we can respect the tunnel design. And what do those results look like? Some results or selected results can look like this. So we've got displacement on the one axis and the time of tunnel excavation. And if we were to take a look at 2 points, let's say at these locations of the tunnel opening, we can determine what the horizontal closure of the wall is in time by taking the relative distance, the relative position of this point, subtract it from the relative position of this point, and determine what that convergence or wall-to-wall closure is, for example. Or we can monitor the roof displacement, how much this roof has moved over time due to either adjacent construction or other factors. So now that we're familiar with these concepts, let's get back to the Eupalinos Tunnel. Once again, we can see the guides and the lanterns that we have in terms of the construction, and this was evident on the one side, but also utilized on the other side. And these served as the control for the excavation works. So the tunnel design consisted of 1.8 meter by 1.8 meter passage for humans, as well as a 4 meter depth at this location, a trough that housed a terracotta pipe that we can see here in cross section. The pipe came in sections that were approximately 72 centimeters long, and had a diameter of approximately 26 centimeters. The pipe increases in depth over the course of the tunnel from 4 meters to from 4 meters deep at the north end to 8.5 meters at the southern end, so that we can get the flow of water from the north to the south. So there's a gradient there. And the vertical shaft links, shafts link the channel to the main tunnel through roughly every 10 meters. So these were dug from the tunnel and then linked together to create the channel that we see here. There were also a number of original ancient symbols that were and letters that were painted on the tunnel walls at various locations in order to denote the tunnel chainage as well as the location of the vertical shafts. So on the west wall, there are letters in alphabetical order at regular intervals of approximately 20.9 meters. Which indicate that this was the basic unit of measurement that was used by Eupalinos. This constitutes 1/50th, so 1/50 of the planned course through the mountain. The size of the opening allowed 2 workers to excavate side by side, and the process must have been exhausting and tedious given the underground conditions for sure. So if we look at the present day alignment of the tunnel, it's not a straight line from the northern to the southern entrance. And why is this? I mean, we can see the northern portal here, we can see the southern portal here, but we don't see a straight line in plan view here. And so why is this the case? Well, if we look at the tunnel in plan view, we can see that the alignment of the northern bore. After about 273 meters from the northern end, an area full of water, rock, and mud forced Eupalinos to modify his plan and direct the tunnel towards the west. Eupalinos planned his redirection using an isosceles triangle with angles 22.5, 45, and 22.5 degrees. And the measuring errors occurred in this determination, and Eupalinos was slightly off course and or significantly off the course that we can see here to the southern tunnel. So that caused for a need for a readjustment of the northern tunnel, and it was redirected to the east at approximately the 400 meter mark. There are three more corrections that we have here that are due to the alignment and readjustment, as well as the geology that was encountered. At the other end of the tunnel, the south, the excavation of the south tunnel was completely straight for 390 meters, after which it diverted up to the east and met up with the northern tunnel. Again, Eupalinos used a unit of 20.59 meters for distance measurements and a unit of 7.5 degrees or 1/12 of a right angle for setting out his directions. And so if one was to look at the tunnel from various locations, here we see a cross section, one sees a heavily supported section to the north with archaic profiles and other Roman profiles, which is characterized by a roof-shaped ceiling formed by stone slabs. On the southern portion of this of the tunnel, what we can see is that there's very little support aside from the portal entrance that has been introduced. And so, therefore, the geology of the area certainly dictated or influenced not only the alignment of the tunnel, but also the construction techniques and support measures that were introduced. So in this way, an observational approach that we still use today in tunneling was certainly utilized. So let's then look at the geology of the area from the macro to the micro scale here. And so Greece is located at the periphery of the convergent boundary between the African plate that is subducting under the Eurasian plate. One of the most earthquake-prone countries on the planet is what Greece is. I mean, it's recorded 32 large earthquakes between 1900 and 2016. So it's definitely on the top 10 list in terms of these types of large earthquake occurrences on the planet. And if we look at the country scale of the geology, we can see the Hellenic arc here. Okay. It's a thrust fault linked to the convergent activity in the Mediterranean ridge. It began propagation in the Miocene and continues to the present day. It's the dominant tectonic activity is this convergent and or related to this vertical alignment. I also bring your attention to the active Californian or Californian fault zone off to the west, as well as the North Anatolian fault, which is very active to the north here. The tectonic thrust direction is from the southwest and the northwest, as seen here as well. And we can see our area of study, which is the island of Samos here. So more local. So The primary resources that were referenced for the geology portion of this presentation came from the following assessments, which were the most recent due to the rehabilitation work associated with the tunnel. These assessments and rehabilitation works needed to be conducted prior to opening the tunnel to the public. As well, of course, such geological assessments are best left to well-educated and experienced geologists. Samos Island is located within the Mytilene-Molassic Basin, which was formed during the Miocene and Pliocene age, or epoch. That's approximately 500 million years ago. And one can see the various formations here in and around the Eupalinos Tunnel area. The aqueduct we can see the aqueduct in this location here. And it was bored mainly through medium bedded to massive limestones, alterations between marl, shales, and platy limestones, as well as tectonic breccia. The geological formations are members of the Hora and Pythagorean or volcanic sedimentary sequences of the Mytilene Mosaic Basin. The Pythagorean fault system, which we can see here outlined in red, is still considered active, and it controls the boundary with the Hora plain. The northwest-southeast direction of this hill range is controlled by the dominant trend of the strata of the Pythagorean and the Hora formations. Those are the most dominant in this region, no doubt. And so these diagrams are the outline of the microtectonic analysis of the tunnel. And so what this shows is that the mean bedding dips are to the north-northeast, but there's limited folding and faulting that have also taken place. This is the geological map and section of the tunnel, also noted as an aqueduct within the literature. So a tunnel or a tunnel aqueduct within the area itself. The majority of the formations that are excavated through are primarily sequences of the Pythagorean and Hora formations, as I mentioned before. And we can see them here, but we can also see them outlined across the cross-section here, or the plan view from north to south. On the south foothill, it passes through the Pythagorean units PY1, which are thick bedded and massive limestones, and the Pythagorean unit PY2, which are thin medium bedded limestones with occasional marl intercalations. On the northern foothill, the tunnel passes through the younger Hora regions. And so here we see the units Hora 1 to 6 successively, and this ranges from platy limestone to limestone with intercalations with marl to slaty thin bedded alternations and massive limestones. And here we can see the detail of the various Hora and Pythagorean formations. And here we can see H1 from platy limestones. We can see the deeper lake deposition here, and can note the more enriched Teflon clastic sediments in the Hora regions. And we also have the Pythagorean shallower lacustrine depositional environment, and what predominates here are the carbonate sedimentation that has occurred. There's 6 alternating lithofacies plus 1 tectonic facies that compose these units, and we can see them here in the chart in terms of the engineering geological characteristics of the rock types and formations that we have. So here we've got the characteristics, and here we've got the lithofacies. And each lithofacy has similar lithology and similar engineering geological characteristics and behavior in the tunnel. The lithofacies that we see here in the blue are medium bedded to massive limestones, and the lithofacies in the brown here and green are the marls, shales, and thin bedded limestones. So from a strength perspective, we're looking at strong to medium to very weak as we move predominantly from left to right on this table. You can see ranges of RQD of 70 to 100% to the tectonic breccia, which we're dealing with very weak material. You can see here 0 to 4%, so very weak material indeed. And we can see here a GSI of 60 to 70, while on the other extreme we can see GSIs of 15 to 25 in some cases. Noting the lithofacies in blue, and we can to massive limestones here, the rock mass is generally massive and well interlocked. They show low hazard of instabilities in the tunnel, and they predominate the Pythagorean units. The lithofacies in brown and green are marl shales and thinly bedded limestones. In these two lithofacies, the rock mass is easily separated along the bedding and contain weak horizons, which means for low tensile and low shear strength. There's also a potential for roof collapses and sliding at the walls of the tunnel. And they predominate the Hora units, as mentioned before. The tectonic breccia is composed by highly fractured rocks, and the rock mass is poorly interlocked. Thus, fragment and block falls are possible, and they occur along major fault zones. However, that being said, over the passage of time, silicification during diagnosis and calciate deposition in later stages have improved the strength and behavior of the overall rock mass in cases. So let us look at the major rock units in the alignment that the alignment crosses. Here's a cross-section of the Eupalinos Tunnel with the alignment between the north portal and the south portal here. And here's the cross-section again for reference purposes as we prepare to examine each of the geological subsections that the tunnel was excavated within. And so if we begin with the southern portion, or the southern portal portion here of the tunnel, and it's outlined with the blue rectangle in the geological cross-section above, we can see the detail of the southern section below here. The construction of the southern portal of the tunnel penetrates the Pythagorean fault zone. And this is probably, and this is it here, this is probably not the most ideal of conditions to begin the tunnel excavation, especially at the portal, as many of you can imagine. About 21 meters of archaic and modern lining were constructed in this region, demonstrating the stability problems that were encountered during excavation and onwards. So this is the main fault plane as it passes through the cross-section of the tunnel, opening in cross-section. Here we can see the southern portal area. And one can see the fault plane as well as the separation of the massive limestone from the tectonic breccia. So the tunnel is characterized by uneven morphology and cave-ins, while failures such as fall of gravels and rocks are definitely possible. In this section, the archaic lining, as seen in the figure to the right here, is covered by colluvial and man-made deposits, MMD, and locally undergoes deformation and fracturing, mainly due to the loose structure of the deep deposits and the low overburden. These conditions provide low self-support of the formation and susceptibility to earthquake movements, leading to overloading on the lining. In the next section, past the southern portal section northwards, again highlighted by the blue rectangle here, the Pythagorean beds gradually sink towards the northern portal, undulating due to successive broad synclines and anticlines. In this section, massive to medium bedded limestones, i.e. the PY1 and the PY2 formations, cover the larger part of the section, providing a stable and generally well-formed cross-section. Minor stability problems are encountered along the major discontinuities and the fractured zones that we have. You can see them here. Horizons of thinly bedded limestones with marl intercalations cover a smaller part in this section, and they are related to one of the main locations of failure that we have in the thinly bedded rock mass that has detached from the roof structure. Here one can see the topography of this section being the section with the most overburden of 170 meters. The photo was taken outside of the main road leading to the southern portal here. In the subsequent section, the boundary between the Pythagorean and Hora formations reaches the roof of the tunnel. And this boundary remains along the alignment of the tunnel without cutting through the tunnel. The northern excavation crew that excavated in this region did so sub-parallel to the orientation of the strata. Detachment and sliding in clay and very fractured rock mass within the overlaying Hora layers did occur. In the next section, a significant change in the formation occurs at the fault at a change of 400 meters. In the tunnel, at approximately 15 meter wide zone of tectonic breccia has formed along the fault, and this yields potential cave-ins and related failures due to the fault. And just adjacent to the fault system to the north, the next section is structured by alternations of strong benches of massive limestone and weak horizons of clay shales and marls. As well, you can see here that there's groundwater follows the impermeable clay and marly horizons, providing minor water inclusion or dripping in the tunnel, and two locations of flowing water. In terms of the tunnel alignment, it should be noted that the first branch of the triangular deviation was carried out at the northern by the northern excavation crew at this location. So their aim was to turn the axis perpendicular to the dip direction of the bedding, and thus the geology then governed such a decision. And this choice provides better stability of the tunnel periphery and quicker passage through the weak and water-bearing horizons. So most probably they decided to make this turn because of the problems, that they had encountered. So in terms of geohazards, in this section there is a potential of observances of detachment and sliding of the weak fissile layers, as we can see here, from the roof and the walls, and also the detachment of block fragments that are occasionally surrounded by clay material. In the next section, in the last section to be talked about, more than 200 meters of archaic and Roman lining was constructed in this section, testifying to the stability problems encountered during construction and also later on. So during the archaic excavation, the sites of the worst geotechnical conditions were faced with the construction of the arduous archaic lining. So lighter problems were faced with temporary support measures. And the archaic lining suffers damages locally, typically from dislocation and or fracturing of the roof members and distortions. And these are mainly attributed to overloading from the surrounding weak rock mass. This is an example of a large instability problem above the Roman lining, which is many meters long. Platy limestones and marls gradually collapsed from the roof, as can be seen here. So now that we've assessed the geology and understood the reasons for the deviations associated with the tunnel alignment, as seen here again, the question remains, how did the two diametrically opposed excavations meet in the middle? Well, on the horizontal plane, Eupalinos calculated the expected position of the meeting point in the mountains. Since two parallel lines never meet, an error of more than 2 meters horizontally meant that the northern and south tunnels would never meet. And so, therefore, Eupalinos changed the direction of both tunnels, as shown here. We've got the northern tunnel and the southern tunnel, that the northern tunnel was turned to the left and the southern tunnel was turned to the right. And this gave a 17-meter wider catching width, so that the crossing point would be guaranteed, even if the tunnels were previously parallel and far away. In the vertical plane, at the start of the work, Eupalinos, as we said before, leveled around the mountain in order to ensure that both tunnels began using the same elevation. So the same elevation at point A and point C, or the northern portal and the southern portal. In order to compensate for any errors in elevation due to the construction process or even the measurement technique, he increased the possibility of the two tunnels meeting each other by increasing, you can see here, increasing the northern tunnel, keeping the floor of the north tunnel horizontal by increasing the height of the roof by 2.5 meters. Okay. While the south tunnel, he kept the roof horizontal and lowered the level of the floor here by 0.6 meters. His precautions as to the vertical deviation provided unnecessary, however, because it shows that there was very little error in the vertical direction. At the rendezvous, the closing error in elevation for the two tunnels was only a few millimeters. And their success. Here's the meeting point of the two bores, the breakthrough at the 426-meter chainage point. And both bores met with an incredible 1.8% accuracy using the mathematics, geometry, and instrumentations that they had at the time. There are certainly other studies of the Eupalinos Tunnel, and here we can see recent studies using modern geophysical and LiDAR scanning techniques by Tsokas et al. And Yoshiteki, respectively, as well as recent restoration investigation of the tunnel by Zambas. I present these here just for those of you that may be interested. So, in conclusion here, the tunnel is open for visitation. So anyone can travel to Samos and be able to go and visit the Eupalinos Tunnel and be able to walk and see the tunnel for himself. So I encourage you to go and visit the Eupalinos Tunnel now that hopefully we've gotten more information about this historical tunnel. The other thing that I'd like to mention here in conclusion is that I would like to make a proposal, and I've already recommended to the Tunneling Association of Canada to acknowledge this international historical tunneling landmark as per other societies, organizations, and learned bodies. And as recently as 2014 at the World Tunnel Congress in Croatia, the ITA recognized it as a historical tunneling landmark. The Technical Chamber of Greece supports, as well as the Greek government. It's already a United Nations or UNESCO World Heritage site. And as you can see with the plaque here, the American Society of Civil Engineers have also acknowledged this international historical tunneling landmark. So I hope that TAC will follow suit, and I volunteer to spearhead that initiative on behalf of TAC. So again, I invite you to support the bid for the Athens WTC 2023 bid, which is spearheaded by the team of Yannis Fikiris rather, and hope to see you in Athens in 2023. Again, I would like to acknowledge all those who made this possible, this webinar possible, As I did at the beginning of my presentation, much gratitude to all of those that have worked behind the scenes and to all of you who sat through and participated through this webinar. Lastly, I'd like to say enida oti uden ida, which means the only true wisdom is in knowing that you really know nothing. There are some selected references, and there's a full reference list available upon request. And I thank you again, all of you, for your kind attention and for allowing me to present at this forum. Thank you very much.